All right, well, we're very happy to have Gheehyun Nahm from Princeton, who is going to tell us about unoriented link Floer homology.
Thank you very much. Thank you for the introduction, and thank you for the invitation. Today, I would like to talk about the connection between Khovanov homology and Floer homology. But before that, I would like to first introduce, in general, Khovanov homology and Heegaard Floer theoretic invariance. Khovanov homology assigns to a link in S3 a finitely generated abelian group, which I will denote it as KH tildle of L. And this is defined in a very combinatorial way. Using an unoriented cube of resolutions. And I would like to say that it's still not very well understood what kind of topological information this measures or contains. And for the experts, whenever I write KH fiddle, I really mean reduced Khovanov homology of the mirror of the link. So in particular, you have to choose a distinguished point on the link to reduce along, but I will suppress that from the notation throughout the first half of my talk. So that is Khovanov homology. So I'd like to introduce Heegaard Floer homology. That is an invariant for close-oriented three manifolds, and it also associates to it a finitely generated abelian group called HF hat. But there's also an invariant for links in three manifolds called link Floer homology. And our convention is that we write this as H of K hat for knots. And then throughout this talk, knots will be denoted as K and links will be L. And this is defined using Lagrangian intersection Floer theory. And also it is, so these groups actually contain some interesting grading information, which I will suppress from the talk. But together with that, it is known that this at least detects some topological information of the knot. For instance, Archibald and Sabo showed that this detects the Seifert genus of the knot and in S3, and also Ni showed that knot Floer homology detects whether a knot in S3 is fibered. So these two invariants are originally defined in very different ways, but surprisingly, there exists connections between them. And perhaps the first such connection was established by Auschwitz and Sabo, where they constructed a spectral sequence from the reduced Khovanov homology of a link in S3 to the Heegaard Floer homology of the double branch cover of the link in S3. And this is over the field of two elements. And in particular, well, this proof is very satisfying and very natural because it really gives you a reason why there might exist a a spectral sequence from Khovanov homology to some link homology theory, some other link homology theory, just like this. Maybe I'll denote that as H of L. And there exists a one-sentence summary, which is that once your link homology theory admits an unoriented skein exact triangle, then you could sort of automatically get some kind of spectral sequence. I'd like to say a few more words about this. So what do I mean by an unoriented skein exact triangle? If I have a crossing of a link L that looks like this, then I could consider as two unoriented resolutions. Which are these two. And let's call the two resulting links L0 and L1. So for example, if I start with this half link, and if I resolve this crossing in the two ways, then I get this as my 0 resolution and this as my 1 resolution, which in this case, both happen to be the unknot. So what does it mean for your link homology theory to admit an unoriented skein exact triangle? That means that whenever I have a crossing of a link like this, then I have an exact triangle that involves the homology groups of these three links. Then Ashworth and Sobel say that very often, especially in that case, you can iterate this unoriented skein exact triangle. And then you get an unoriented cube of resolutions of this link homology theory. And then this will be like the unoriented cube of resolutions for Khovanov homology, but maybe with extra differentials. And so you get a spectral sequence. To your wanted link homology theory, H of L. And now what's left to show is that you want to check that the E1 page of the spectral sequence is isomorphic to, say, the Khovanov chain complex. And that boils down to checking that Khovanov homology and your link homology theory agree for very simple types of links and maps between them.
Yep. What's the next stage of the cube besides the triangle?
Yeah, that's a great question. So one way of thinking about this is that instead of thinking about this triangle, maybe what you really want to do is you want to find the chain map like this, such that the mapping cone of this chain map is, say, quasi-isomorphic to the chain complex for L. And so from this perspective, what you do in the next step is if you have two crossings, then you can resolve the two crossings using these two possibilities. And maybe I'll call, so maybe for the half link, it'll be something like this. maybe I got the conventions wrong, but you want to say that this iterated mapping cone is quasi-isomorphic to this chain complex. So this would be the second step of iterating your unoriented kinetics abstract. More questions?
Or so how do you get a spectral sequence out of this?
Oh yeah, that's a great
This
question.
may be a silly question because I don't know anything about spectral
Oh,
sequences.
no worries. So for this case, so you consider the filtration given by this. If you use this filtration, then the E1 page will consist of the direct sum of the homology groups here of these four things, and then the differential will just be the chain map on homology induced by the four edge maps. So actually, I like a bit. In general, these edge maps won't commute on the node, but only up to homotopy. So you have to add a homotopy to make this into a chain complex.
Oh, okay. So the filtration is algebraic or something.
Yeah.
Got it.
Yeah, the filtration is, yeah.
And if you have a, say, n-dimensional cube, then how do you push that down onto a
Oh, yeah. So the vertices of the n-dimensional cube will be labeled with some zeros and ones, and you add the ones. You count the number of ones.
Oh, okay.
Yeah.
Yeah.
So the filtration, the I filtration subcomplex will be the direct sum of the vertices with that number greater than or equal to I. Okay, then I would like to move on to special case of connection between Khovanov homology and Heegaard Floer theoretic invariance, and talk about Rasmussen's conjecture. Where he conjectured that the rank of reduced Khovanov homology of a knot in S3 is greater than or equal to the rank of knot Floer homology of that knot. And this should come from a spectral sequence from this to this. And one reason why you might be particularly interested in this particular statement is that this is in some sense stronger than other similar statements like that. Because assuming this using well-known properties of knot Floer homology that is related to it detecting the cipher genus, you can show that Khovanov homology detects the unknown. Which was famously shown by Kronheimer and Rofka. Using a different method.
So the idea here is for the unknot, the rank is 1 or something.
Yeah, and for all the other
The
knots.
rank of K is 1, which means the genus is 0, which means it's the unknot or something.
Yeah, so you have to use an extra symmetry. So if the so knot Floer homology has an Alexander grading, and Alexander grading I is the same as Alexander grading minus I. And so if your knot is not the unknot, then it has something in Alexander grading G, where G is the cipher genus, and so it has something in Alexander grading minus G as well. So the rank is at least 2.
Oh, okay.
Okay. Oh, so this conjecture was proved by Dowlin over Q And this is an amazing result, but maybe compared to like the double branch cover spectral sequence of Ashworth and Szabo, there's really no sort of one sentence summary of the proof in some sense. Oh, sorry. Dowling uses oriented cubic resolutions defined by Ashworth and Szabo and Manolescu and Belyakova, Plutira, Robert, and Wagner fixed design. But unlike that spectral sequence, it's not like you have a cube of resolutions for Nahm-Floer homology and then you're suddenly done. This involves some clever change of basis argument. And so the proof does not work for fields of characteristic 2. And also you need some additional technical condition on the singular grade that you start with. But maybe it is a bit unreasonable to expect something like in the spirit of Ashworth and Szabo's spectral sequence for Khovanov homology to Nahm-Floer homology. But in fact, there exists a spectral sequence just like that, defined by Cronheimer and Mrozka. When they showed that Khovanov homology detects the unknot, the only problem, if you want to answer Rasmussen's conjecture, is that the thing their spectral sequence converges to is not quite Nahm-Floer homology. Instead, what they get is for links in 3 manifolds, they define another link invariant called I natural of a Y and L using sort of instanton Floer homology. And they actually construct sort of the unreduced version, which I will talk about a bit later, called I sharp. And these invariants happen to be the right Floer theoretic invariants from the view of Khovanov homology. Well, there exist unoriented sky and exact triangles, and you can iterate them. And so they get spectral sequences from reduced Khovanov homology to I natural and unreduced Khovanov homology to I sharp. And moreover, I said that this is maybe very similar to Nahm-Floer homology. Indeed, when they show, assuming this, that Khovanov homology detects the unknot, they use basically the same argument using similar properties that I natural has compared to I sharp, compared to Nahm-Floer homology. And in fact, they conjecture that the homology groups are isomorphic for knots over Q. So maybe we could do something similar in Heegaard Floer homology as well. But this turns out to be quite tricky. The main point is you want to find sort of the right link homology theory. So you want the right Heegaard Floer theoretic link homology theory. Maybe let's call it H of L, such that you can run this argument of iterating first defining an unoriented sky and exact triangle and iterating it to get a spectral sequence. And secondly, you want this invariant to be the same as not Floer homology for knots. But this turns out to be tricky because although there exists a natural generalization of not Floer homology to link Floer homology, that does not work. And indeed, it fails for exactly this example here. There just cannot exist an unoriented sky and exact triangle. Oh, sorry. Because the rank of link Floer homology for these three links are 4, 1, and 1. So they do not satisfy the triangle inequality. So the three homology groups cannot form an exact triangle.
So is there an oriented sky and exact triangle or?
Yeah, so I haven't thought about it very much, but so not Floer homology categorifies the Alexander polynomial, and so there exists a sky and exact triangle that categorifies the oriented relation that the Alexander polynomial satisfies.
So what does that mean? Like you only have an exact triangle between certain parts of the grading? Or the...
So the oriented thing is like instead of having these three links, you have links that are related by this.
Yeah, I guess right. So, wait, no, I was just asking about your last comment that did you say there is something that categorifies the Alexander polynomials?
Yeah. So there exists. So
that something is not just HFL or.
Oh yeah, sorry. Yeah, this categorifies the Alexander polynomial, maybe normalized in a right way, but the Alexander polynomial already does not really have an unoriented sky relation. Sure. Yeah. Whereas Khovanov, the Jones polynomial does.
But yeah, that's what I was confused about. But so HFL doesn't have an oriented skein exact triangle.
Oh, sorry, it has an oriented skein,
Oh,
exact triangle. But it does not have an unoriented one.
okay.
Sorry. And yeah, oh, indeed, Rasmussen's conjecture does not hold as stated for links in general, because the rank of reduced Khovanov homology is 2 for the half link. So this rank inequality does not hold. So the real key step is you want to define a suitable generalization of Floer homology for links, such that it has an unoriented skein exact triangle. And maybe the first try link Floer homology is not the invariant that you work, invariant that you want. And now I'd like to state the main result. For links in any three manifolds, but let's only talk about links in S3. For simplicity, we define Heegaard Floer theoretic invariance called HF natural of the link, HF sharp of the link, and HF double sharp of the link, such that you can iterate. There exists an unoriented skein exact triangle for all of these theories, and you can iterate it. And you get spectral sequences from reduced Khovanov homology to HF natural, Khovanov homology to HF sharp, and another version, the minus version of Khovanov homology given by the Lie deformation to HF double sharp. And maybe I will say a few words about what this is later. And secondly, indeed, for knots, HF natural of the knot is exactly the same as knot Floer homology. Oh, sorry. And I work over the field of two elements. And so I get the spectral sequence from reduced Khovanov homology of a knot to the non-Floer homology of the knot.
So this gives the Rasmussen conjecture over Simon 2.
Yes, that's right. So I would like to make a few remarks. First, these Heegaard Floer theoretic groups are not some artificially defined groups. They're actually a small variant of the unoriented link Floer homology defined by Oshwas, Stepchens, and Sabo. And so I call these homology groups unoriented link Floer homology as well. Secondly, as Rohel mentioned, I get a rank inequality over F2. Which is new. But also it is conjectured that not Floer homology does not have torsion. So by universal coefficients, this rank inequality over F2 is conjectured to be weaker than the rank inequality over Q. But in my opinion, although this is new, the real main contribution is noticing that this variant of unoriented link Floer homology is the right Heegaard Floer theoretic link homology groups to look at if you want spectral sequence from Khovanov homology to not Floer homology, and constructing these unoriented sky exact triangles and iterating that. And if I have time, I would like to talk a bit about how I found these homology groups, because I found them by trying to find a Heegaard Floer analog of these instanton Floer theoretic homology groups. And indeed, these should be thought of as Heegaard Floer analogs of this spectral sequence.
So the rank inequality is conjecturally weaker because HFK doesn't have torsion, but Khovanov homology might have torsion.
Yeah, Khovanov homology has torsion.
Oh, okay.
Yeah.
Oh, so then you would pick up the torsion on that side, but
Yeah.
not on that side.
Yeah, but yeah, I think it's not known whether a not Floer homology has.
Oh. Why do people think it doesn't have torsion?
People are very good at computing this I think people could compute it for like 40 crossing knots by Sabo's program. And so far, there's no known torsion at all.
So if I asked a large language model whether it has torsion, it would say no or something.
Probably. Yeah, that's a very interesting problem. Yeah, so throughout the second half of my talk, I would like to define these Heegaard Floer theoretic groups, unoriented link Floer homology, and compute it for the half link to demonstrate that it indeed has rank 2. But before that, maybe I should pause for questions.
So, I mean, is it expected that these spectral sequences follow from, maybe say, one homotopy type is same as the other filtered homotopy type?
Oh, that's a great question. Yeah, so I should first say that I don't really know anything about the homotopy type, stable homotopy refinements, but does it exist in like the minus version of links? Because I kind of have to use some of the U variables to construct. So I need more information than just the hat version to define these. So yeah, but yeah, sorry, I'm not really.
So, I mean, what's the general, like, why would one expect such spectral sequences to exist?
For the homotopy refinements, or
Just for homology?
Yeah, that's a good question. yeah, I don't quite understand it very well, especially because maybe not Floer homology is like, but for me the way I think about it is that there exists an unoriented skyne exact triangle, and so this sort of suggests that there should exist a spectral sequence. But the reason why there exists such an unoriented skyne exact triangle is slightly mysterious for me. Yeah. Um, so I should also mention that Manolescu defined an unoriented exact triangle for a modified version of link Floer homology, which is for links with extra base points. And so it sort of increases the rank. And I don't quite understand how my unoriented sine exact triangle is related to his version. Yes.
Is there like an instanton version of your spectral sequence from KH minus?
Oh, that's a great question. I don't know. Yeah, with that, yeah. Yeah, maybe there is, but I haven't done the literature research. Now I would like to move on to define these link Floer homology groups and hopefully convince you that maybe the definitions seem pretty natural. But before that, so there's three different homology groups that I want to define. And the definitions are partly motivated by the corresponding three different Khovanov homology groups. So I would like to first introduce these Khovanov groups to draw parallels between them. So until now, I've been mostly focusing on the reduced version of Khovanov homology. But perhaps the version that we are more familiar with is the unreduced version, which is like the default version. And the chain complex of that is a free chain complex over Z. But actually, there exists sort of a more general version called a minus version, from which you could define this. This was defined by Lee and further studied by Drake Rasmussen. I'm not sure. Where he used the minus version to define the S invariant and give a combinatorial proof of the Miller conjecture. And this minus version is gives a chain complex, maybe I'll call it CKH minus of L. And this is a free chain complex over Z adjoined one variable, one formal variable U. And so indeed you can, so I will explain how you define this unreduced version and the reduced version from the minus version, because that'll be exactly how I would define H of natural and sharp from H of double sharp. But to do this, we need extra structure on this, which is the base point action. So if we have a point P on the link L, then Heaven and Ni define the base point action, which I will denote also as P, from which is an endomorphism of the chain complex. And they show that if two points are on the same component, then these induced endomorphisms are chain homotopic. Oh, and also, almost by definition, you get that p squared is strictly equal to multiplication by the variable. Okay. And so if L has L components, then we can choose a point on each component. So let Pi be on the ith component. And then the chain complex becomes a module over Z adjoin one variable for each point. And the actions squared are all the same. And actually, these actions are strictly commute. So it is indeed this module. And for concreteness, I would like to also mention that this is the Khovanov homology of the L component only. So now I would like to explain how we define the unreduced version. This is just defined by quotienting out the minus version by the variable u. And the reduced version, well, to define it, we need to choose a distinguished point. And then the reduced version of the chain complex is defined by quotienting out the minus version by the base point action corresponding to the component that the point is in. So maybe it's good to mention that for the unnods, the rank of unreduced Khovanov homology is 2, and the rank of reduced Khovanov homology is 1. Now I would like to define the unoriented link for homology groups. But before we actually define them, I would like to introduce or set the stage and talk about the most general version of link for homology, because our unoriented link for homology groups will be defined from them in an algebraic way, algebraic modification. This link for homology was defined by Arshus and Sabo, and the not version was independently defined by Jake Rasmussen. And how is it defined? Well, let's work over F2. And let's specialize for links in S3. So to define these Heegaard Floer theoretic homology groups, you have to add base points on them. And in this case, we put two base points, Zi and Wi, on the ith component of the link. And then we choose a Heegaard diagram to cook up an auxiliary symplectic manifold. Maybe let's call it M, which is some symmetric power of the Heegaard surface, and also two Lagrangians. Maybe I'll call it alpha and beta in M, which are the tori given by taking the product of the alpha and beta circles in the Heegaard diagram. And then the most general version of link Floer homology, called curly HFL, I'll define the chain complex, is defined as the Lagrangian intersection Floer homology of alpha and beta in this symplectic manifold M. But we work over the ring R, which is given by adjoining one variable for each of the base points. So the chain complex as a module over R is freely generated by the intersection points of alpha and beta. And now the differential counts index 1 pseudo-holomorphic curves. But these base points here on the Heegaard surface gives rise to divisors on this symplectic manifold. So when you're counting these curves, we assign weights to these divisors. So we count the divisor given by Zi with weight large Zi, and Wi with weight Wi. And for the experts, there's another popular convention where the weight for Zi is called Ui and the weight for Wi is called Vi. But I will use this convention. And indeed, the version of link Floer homology that I have been talking about, HFL hat, is the homology of this chain complex, which is just given by quotienting out this chain complex by all the variables. And I would like to do some examples. So maybe I could start doing the example of the Hopf link. So let's consider this Hopf link in S3. And to define the link Floer chain complex, we have to put two base points on each component. So maybe I will put base points like this. And then we have to draw a Heegaard diagram for this link in S3. Turns out that for this one, there's a nice simple choice. So the underlying Heegaard surface will be S2, and the alpha curve will be this circle, and the beta curve will be this circle. And the base points will look like And in this case, the auxiliary symplectic manifold is actually just this Heegaard surface S2, and the Lagrangians are also just these circles. And so CFL is given by there's 4 intersection points. So the link flare chain complex has 4 generators over the ring R. So maybe I'll write it like this. Where R is this ring. And for the differential, we count bigons. For instance, here there's a bigon from A to B that goes through the base point Z1. So this has weight Z1. And so we have a differential from A to B with weight Z1. There's another bigon from A to D here that goes through the point at infinity, which has weight W2. And there's a bigon here from C to D with weight Z2. And a bigon from C to D with weight W1. And there's more bigons, but they cancel in pairs. So this is the chain complex for CFL. And to obtain the chain complex for CFL hat, we quotient this out by all the variables. So the chain complex will be just 4 copies of, it will be a vector space with dimension 4, and the differential will vanish. And so the rank of its homology is also 4. And that was bad for us. We wanted 2. So now I would like to define unoriented link flare homology. Similarly to Khovanov homology, I should define the minus version. And the other versions will be defined as similar algebraic modifications. Oh, but before that, I forgot to make a remark that in this curly chain complex CFL, maybe it's a bit hard to see from that example, but multiplication by Zi and Wi is homotopic, chain homotopic to multiplication by Zi and Zj and Wj. And the convention is that you call the product of Zi Wi Ui, and the product of Zj of Wj as Uj. And because multiplication by Ui and Uj are homotopic in the chain complex, once you pass to homology, then there's a well-defined U action on homology. Okay, so I'd like to come back to defining the minus version of unoriented link flare homology, which we call HCF double sharp. This is defined by quotienting out the most general version of link flare homology by setting Zi equals Wi.
Sorry, I have a question about your U action. So geometrically with the UI action, should I think of it as like counting index one curves that pass through the component Li of like a single point double? Like what?
Yeah, that's a good
Like
question.
it seems like if you have a non-algebraic contribution from this, then you have some index one curves through Zi and Wi, and then if you put them together, then they get onto one. Or, I don't know.
So yeah, I'm not sure how to think of this in terms like by curve counting. This is I guess I just think of it as just multiplying the chain like
Yeah,
I'm not
there might be nothing there. I was just curious. Yeah.
yeah, that's a good question. I'm not sure. Okay, so in this version, so we are setting Zi equals Wi, and the convention was that their product is Ui. So let's call them Ui to the 1/2. And now because all the UIs are chain homotopic, so this is a module over f adjoin all the variables where we quotient out by identifying their squares together, which is just like Khovanov homology. Oh, maybe I erased that. And similarly, this is actually the same, actually just the minus version of unoriented link Floer homology of the L component only. And we call multiplication by Ui to the 1/2 the base point action corresponding to the ith component. So for instance here, CF double sharp will be given by 4 copies of the ring R, where R is just f adjoint U1 to the 1/2 and U2 to the 1/2, where we set Zi equal Wi equal Ui to the 1/2. So this is our chain complex. And now I would like to define the reduced and unreduced versions from the minus version, just like how we defined them for Khovanov homology. So for the unreduced version, which you call CF sharp, we quotient out by the U variable. And because all the U variables are chain homotopic, we can indeed just quotient out by any one of them, let's say U1. And if you choose to quotient out by some other variable, then it'll result in a quasi-isomorphic chain complex. Okay. And for the reduced version, we have to choose a distinguished point in the link, and we'll define the reduced version by quotienting out this chain complex by the corresponding base point action. So let's compute this for the hot link. So let's put the distinguished point here on, say, the second component. Then we quotient out this chain complex by U2 to the 1/2. So the base ring will be f adjoint U1 to the 1/2 Um, and then these diagonal differentials all cancel, but the horizontal ones remain. And so if you pass to homology, then it has rank 2 supported here and here. Okay, I ran out of time, so yeah, maybe I'll stop here.
Questions? I have a question. Well, I have a two-part question. So I guess one is that there's this conjecture about, you mentioned about HFK being to the instanton invariant, or at least having the same rank or something. So, do you think that's also true for links, or is there just a counterexample?
Yeah, that's a great question.
Or I guess with links using your version of the link.
Yeah, yeah, that's a great question. So, I didn't have time to mention this, but one reason why I said that these seem to be Heegaard Floer analogs of I natural and I sharp is because actually the way I found these invariants is by trying to come up with a Heegaard Floer analog of Bott's recent two-surgery exact triangle in instanton Floer homology. So there's more sort of structural similarities between these instanton Floer theoretic invariants and Heegaard Floer theoretic invariants. Yeah, for instance, if you have a knot in S3, then an exact triangle holds like this actually holds for any knot in any 3 manifold. So Bott shows that there's an exact triangle like this. So I show a Heegaard Floer analog where these are replaced by HF hat and this is replaced by HF sharp. Yeah, so it seems like they should be related, but yeah, I don't think I personally don't really know much about instanton Floer homology to make the conjectures.
The second part of my question is, well, if I remember right, this I sharp is defined. Well, there's a stabilization step, like you connect some with a theta graph.
Yeah. So
I
yeah.
was wondering if you can. Well, to me at least, because I don't know anything, your construction seemed completely different. I was wondering if it could be that way.
Yeah. So I don't really understand instanton Floer homology, but there's one sort of maybe a more general version, which I don't quite know the Heegaard Floer analog, but so I sharp is given by you have your link and then you add a half link away from the link and choose some arc between the two components. So
which is the theta graph, or that's like one of the singular ones.
I'm not really sure about
that.
but so this is maybe I sharp, whereas I natural is like you start with a distinguished point on your link and then you connect some like this.
Okay.
And actually, I guess this is kind of similar to Khovanov homology if you view the unreduced version as like you add an unknot away from your link and then you put a base point on the unknot and then you take reduced Khovanov homology of that. And if you think of it like this, then the unreduced and reduced versions of unoriented link Floer homology are kind of similar structurally.
Oh, Well, but in the link Floer homology, you're not modifying the link or anything.
No, but yeah. So, but
Starting with a link and adding a off link or something.
yeah, but
That's what I was confused about.
you can kind of define it sort of like that. So,
Oh, okay.
so what I think maybe one way of thinking about it is like, if you have a distinguished base point like this, then they sort of consider this meridional component, and then they do some incidental Floer homology of this. So it's like you have to. Yeah, so you don't see the half length from the picture, but you can sort of define HF short by adding a sort of trivial unknot away from the link and then sort of putting a base point on that. And yeah.
Okay.
Those are very formal. It's not like I'm not really making much mathematical statements. They're sort of formal things.
Yes. Okay. Right. Let's thank Gheehyun again.